Hello, everyone. Welcome to video one of wave physics. Today we're going to be talking about how to model sinusoidal waves. Let's get started. So as a recap for where we were last week in the intro video, we talked about what waves are, how we define waves, and some examples of waves, and also an outline of the topics we're going to cover in this video series. And so an outline for today's video, we're going to be talking about the vocabulary for wave properties, the terms we use to describe waves. We're going to be talking about how to represent waves both mathematically with equations and graphically. And we're going to learn how to link the wave equations and the graphs to the properties, the vocabulary, the terms. So first, let's look at this picture of a transverse wave. And so if you remember, a transverse wave is a wave where the direction of oscillation, which in this case is up and down, is perpendicular to the direction of propagation. So in this case, we can assume that the direction of propagation is from left to right. So this is a snapshot of the wave at a fixed time, and so we can imagine this is what the string looks like at a fixed time if we assume it's a transverse wave on a string. And so time is not changing, but as you know, the left to right, that represents a different position along the string. So some terms, the crest is the term that you use to describe these peaks up here at the the maximum positive amplitude, and the trough is the term that you use to describe the the maximum negative amplitude, or the negative amplitude with the maximum magnitude. And so the wavelength represents the distance from a crest to the next crest. It's also the same as the distance from one trough to the next trough. More generally put, it's the distance, the width of one full cycle of the wave. And so you can get that from the crest to the crest, you can get that from the trough to the trough, you can get that from any two identical points where if you traverse from here all the way back to here, you are now one cycle ahead of where you started. And since this is a sinusoidal wave, it's periodic, it happens in cycles. And then the amplitude is the maximum displacement from the center. And so this distance right here, that displacement, that is the amplitude. And the amplitude, is the same whether you look from a crest to a midpoint or from the trough to the middle. So amplitude, we represent that with the letter A or with Y max, and we'll talk about why we use Y max when we start talking about the equations. Wavelength, we represent with lambda, yeah, so here we have now we're no longer looking at a wave at a fixed time. Now we're looking at the wave both in position, in space, and with increasing time. And so this wave is traveling from left to right. And so now we can talk about some additional properties as well that have to do with time. So one is the wave speed, which is the speed that the wave propagates through space. And so if I take my cursor and I track one of the crests as it moves from left to right, that speed at which my cursor has to move to keep up with the wave, that is the wave speed. And we represent that with the letter V. The frequency is the number of cycles that passes through a given point per unit time. So if I put my mouse here, my cursor here, I can count 1, 2, 3, and I'll actually take out a timer and count this. So I can count the number of cycles that will pass in a certain amount of time. So let's let's take 10 seconds and let's count how many cycles will pass. So 1, 2, 3, 4, 5, 6. And so that was 6 cycles in 10 seconds. So the frequency would be about 0.6 cycles per second if you divide 6 by 10. And so we express that in terms of seconds to the -1, which is also equivalent to hertz. So it's cycles per second, which is why second has a negative exponent. So that's the frequency, and we express that with the variable f. And the period is the amount of time it takes for one cycle to pass. And so we represent that with a capital T. And if I take out my stopwatch again, I can record how long it takes to go from one crest to the next crest, from one cycle to the next. So I'll start the timer now, and I'll end the timer now. And so that was a little less than 2 seconds. And so the period would be a little less than 2 seconds. And so that is similar to the fact that, we had about 0.6 cycles passing per second. And the relationship between the frequency and the period is that they're inverses. If you notice that the frequency has units of seconds to the -1 and period has frequency of seconds, they're actually the reciprocals of each other. So if you know the frequency, you can calculate the period by doing 1 over the frequency or vice versa. So I was talking about transverse waves, but these properties also apply to longitudinal waves as well, even though they might be harder to see, or you would see them differently. Um, so the wavelength here, similarly, is the distance from one crest to another crest. In this case, the crest, you don't see like an up and down, but since it's the longitudinal wave, you can see what would be similar to crests in terms of the most compressed parts of the wave, these compressions. So if you take the distance from one compression to the next compression at a certain point in time, that would be the wavelength. You can also do, this part in the middle is called a rarefaction. It's very empty. We'll talk about that later. It's where there's, the least number of, there's the lowest pressure. That would be, similar to a trough. If you just take the distance from one trough to the next trough, that also gets you the wavelength. We can also talk about the wave speed. If I use my cursor to keep track of how fast, this compression moves from left to right, that also is the wave speed. We can talk about frequency by putting my cursor here and counting the number of cycles that pass through unit time, or the period by counting how long it takes for one cycle to pass. The hardest part to see here maybe would be amplitude. And so there are different ways to express amplitude for a longitudinal wave, but one of the ways, and we'll talk about this later once I start talking about sound, one of the ways is you can see, if you look at these particles, and I brought this up last video, you can see that these particles, these individual particles, are moving back and forth in the same place. Even though the wave looks like it's moving left to right overall, these individual particles are having their own oscillatory displacement. So we can say that the amplitude here, the displacement amplitude, is the maximum displacement that a particle reaches from its middle point. So if a particle's middle point is right about here where my cursor is, then that amplitude is that maximum displacement. So that would be the amplitude, the displacement amplitude. There's also pressure amplitude, and I'll talk about that in a future video. But in short, the same terms apply whether to a transverse wave or to a longitudinal wave. So how do we model a sinusoidal wave mathematically? So right now, this wave is changing with both x and t. So changing in both space as you go from left to right, and in time. As time passes, the wave moves, and so the displacement at a certain point is always changing. So we don't want to deal with two variables at once first. We just want to deal with one. So let's set time constant. Let's take a snapshot of this wave in space at a certain time. And now it's no longer moving. Now we have this snapshot at some set t, and now we can only worry about changing x. So if we plot that, we can get a sinusoidal wave graph, a sine wave, that shows the amplitude as a function x, as a function of position in space, left or right. And so to model this with an equation, we can use the equation y equals sine of x. And t is fixed, so t is not changing. But this equation is not good enough because y equals sine of x defines a very, it's a very unique, it's one wave, it has like a fixed amplitude, a fixed wavelength. But there are lots of different kinds of waves. They can have different amplitudes, wavelengths. So we need to expand our model to account for the fact that these parameters can be different. So this equation is not enough. So let's start with the amplitude. Different waves can have different amplitudes. So the sine oscillates from 0 to 1 to -1 to 1 to -1, but you can have waves that go from 2 to -2 or from 0.5 to -5. So to do this, we introduce a term called y max, which is the amplitude, as I mentioned earlier, in front of the sine x, and that will scale the sine, up or down. It'll expand it or compress it vertically, which changes the amplitude of the wave. So as an example, if I had an equation that was like y equals 0.5 sine x, and the one plot in red here is y equals sine x, then if I draw that, y equals 0.5 sine x, the amplitude would be cut in half. So you get something like this. And so, that amplitude is now about half of the original amplitude. And so, yeah, y max is the amplitude. Clear the drawing. So that's the amplitude, and then there's also the wavelength. So if we look at a wave in space, the wavelength of the wave can also be different. The wavelength is the distance spanned by one cycle. So for the distance from here to here. So to introduce that, we need to change the rate at which a change in x will bring you from one cycle to the next. In a wave with a very long wavelength, such as like something like this, x has to change a lot in order to go from one cycle to the next. But in a wave with a very short wavelength, x only has to go, a small amount to go from one cycle to the next. And so we know that sine, returns, it completes one cycle when the argument increases by 2 pi. So since x is, inside the sine function right now, we account for this by introducing this scaling factor kx. So x is multiplied by k. And if you notice, so if you think about if k was 1, then x has to go from 0 to 2 pi in order to get from here to here. That's one cycle. So in that case, the wavelength would be 2 pi. But if k was 2 pi, then x would only need to go from 0 to 1 in order for this whole product to go from 0 to 2 pi and for the sine to complete one cycle. So there's an inverse relationship between k and lambda here, the wavelength. And so lambda is equal to 2 pi divided by k. And so you can see that as the wavelength increases, you need a smaller value of k because that will cause x to traverse, that will require a greater increase in x before you complete one cycle. So there's an inverse relationship between lambda and k. And k is what we call the angular wave number. Okay, so we talked about amplitude, we talked about wavelength. Those are pretty easy to visualize. Something that might be a little harder to grasp at first is the concept of phase. And so we have a wave that looks like this, but what if we had a wave, what if at a different time we took a snapshot of this wave and it had the same amplitude, it had the same wavelength, but it looked something like this. That's not a great drawing. But or maybe something like this. It was just shifted over a little bit. Sorry, I'm drawing with the trackpad here, so it's not great. But if it was just shifted over a little bit, then the amplitude and the wavelength are the same, but we have to account for that shift. And so to do that, we introduce this this constant, this additive term inside the sine function, and this will shift the sine function over. And so if you think about so this is phi, which we call the phase. And if you think about if phi is a negative number, that means that x has to increase in order for this whole value to be the same, which causes the sine to be the same. So if phi is negative, that means that the whole sine wave will shift a little bit to the right because x has to be a little greater in order for the values to be the same. But if phi was negative, then you get a shift to the right like the one I just drew. But if phi is positive, that means that x has to be a little smaller in order for that value to remain constant. And so that would shift the entire curve to the left. So if phi is positive, you get something like that that looks like this. So that's the phase. Okay, so we've looked at the amplitude, the wavelength, the phase. So we've looked at these properties when we plot y versus x, y versus the position in space. But what about time? So we've looked at one variable. Now let's look at the other. So how do we convert this to a graph of y versus t? And so what we can do is we have to pick a fixed value of x. We looked at y versus x with a fixed value of t, so now we have to do the other way around. We have to fix the value of x and vary the value of t because we don't want to deal with two variables changing at the same time. Not yet. So let's pick a fixed point where x is constant. So for example, let's just kind of like record the displacement at this point. I'll put my cursor here. And then assume the wave travels from left to right in the positive x direction. So as t increases, the wave will travel from left to right. And so if you kind of imagine, this part of the wave will go through first, followed by this part of the wave, which will go through to the right, and then this part of the wave will go through to the right. So the cursor will go up, and then down, and then up, and then down, as this wave passes left to right through that point. And so we can, now we take that, and now we get a curve for displacement y versus t, and this also looks like a sine wave. So I mean, I use the same shape from the previous slides, but this actually represents something different, and it doesn't always. It's still a sine wave, but it can look very different depending on your scale for the axes. So it's the same shape, but it represents something different. This is displacement versus time at a fixed point. This is not displacement versus position at a fixed time. That was what I showed previously, but now time is on the horizontal axis. So if I put my cursor here and I trace it up and down, something to note here is that my cursor is tracing, as t increases, my cursor is tracing the wave in the opposite direction as if t was fixed and I increased x. If t was fixed and I increased x, I would trace the wave like this, left to right. But here, it passes, as it passes through left to right, I'm the parts that are toward the right, my cursor is encountering that first. So my cursor is tracing it backward from right to left. So that's why when we introduce t into the sine function, it has the opposite sign of x. So we put sine kx minus t plus phi, but this doesn't account for the wave speed. If I had a wave that was moving much faster, there would be many more cycles passing through for a given value, for a given change in t. So we need to account for that as well, and to that we introduce this constant in front of the t called omega. And so that will change the rate at which a change in t affects your position affects the displacement. So now let's look at period and frequency, because these are time-dependent properties, and so we have to model them based on our displacement versus time graph. So we have our equation this is our full equation for the wave as a function of position and time. And so from the graph of y versus time, we can just pull the period right off that graph. The period is the amount of time it takes for one cycle, a full cycle, to pass through a point. So similar to how we got the wavelength in the y versus x plot, we can get the period by looking at the time it takes for this one cycle to pass through our fixed point. So that would just be this span of time right here. That's capital T, that's the period. And something important to note is that when t increases by t, when t goes from here to here, omega t has to increase by 2 pi, because that is what brings the sine back to the same value. So imagine if we started here and t increased by t and went here. The next time that we could get the sine function to return to the same value at this peak here is if you go through one full cycle, is if omega t increases by 2 pi. So we can create a relationship out of that where omega times delta t, which is capital T, the period, omega times capital T is 2 pi. And then we can divide both sides by the period to get omega equals 2 pi divided by the period. And so this is how you can obtain the value of omega just based on a graph of the displacement over time. And so omega is what we call the angular frequency. And if you remember, the frequency is the reciprocal of the period, and so since omega is 2 pi over t and f is 1 over t, we can also express omega equals 2 pi times f. And so if you know the frequency, it's very easy to determine this coefficient, or if you have the equation, it's very easy to use this relationship to just calculate the frequency. Okay, so that was a lot. So what have we learned? So we've learned the vocabulary for waves. We've learned about amplitude, wavelength, frequency, and phase. We've learned how to represent these mathematically in the sinusoidal wave equation and what these different parameters in the equation represent. So our full equation is y as a function of x and t equals y max, the amplitude, the maximum possible displacement, times sine of kx minus omega t plus phi. And so phi is the phase, k of x is allows us to determine how the position affects our displacement, and omega t determines how the particular time or a change in time, how that affects our displacement. And so next video, I'm going to expand on this a little more to talk about wave speed and how do we apply this knowledge to graphical representations of actual waves. And so I'm going to work through an example of applying these terms and this equation to some graphs to figure out how would we calculate these terms if we were given some actual data. So that is all for this video, and see you in the next one.